Hello students, happy to be able to reach to you all. The first thing which I want to say is, which I have already written on the board, you can see at the top, let us all fight against corona. So let us all make efforts, whatever efforts we can to fight against corona. So in an effort to fight against corona, I have just prepared this video lecture so that you are benefited and your studies are not hampered, and I am able to teach you in the same way as I would have done if I would have taught you in a classroom. So let me start with the chapter 3. The title of the chapter is Mathematical Models. Now in this chapter we are going to model some mathematical problems. We are going to find equations governing those mathematical problems. And the first problem that I am going to discuss with you all is problem of vibrating string. And this article can also be called as a derivation for the one-dimensional wave equation. So if in the exam, if you are asked to discuss the problem of vibrating string, or if you are asked for a derivation of one-dimensional wave equation, this is the article which you have to present in the exam. So let me start with the problem of vibrating string. Now coming to the first thing, what is the problem? The problem is that we have to consider the vibration of a stretched string of length L fixed at the endpoints. What we have is, there is a string like this, and we are assuming that the length, there is a string, let me rub this off, there is a string like this which is tied at the two ends. The two ends are fixed, which means it is tied at the two ends, and we are assuming that the length of the string is L. So, and what I am doing is I am plucking the string, I am giving a vibration to it, and the string starts moving up and down. So such problems come in real life. For example, this problem is just comparable to, if you have a look at this guitar, and if you just consider your string to be this, which is tied at two ends. This is one end, this is the other end. So this string is of some fixed length, it is tied at two ends, and you are, when you are playing the guitar, you are plucking it, and when you pluck it, there is a vibration in the string and it starts moving up and down. So this problem is just comparable to this one. So consider the problem of vibration of a stretched string of length L, which is fixed at the endpoints. Basically in this problem what we are going to do is, we are going to derive the equation of motion. I am going to derive the equation of motion which determines, or which finds the position uxt of the string at time t after an initial disturbance is given. Now this was the original string, and you are plucking it, you are applying force on it, and when you apply force on it, the string starts moving up and down. And let us suppose that this is how the string moves. It goes up, it goes down, it goes up and down, and it is fixed at the two ends. Now I am interested in finding out what is the position of this, any element, what is the position u, I am denoting the position by u, what is the position of any element of the string when the time is t, and when the horizontal distance, if you take the horizontal distance, if this element, the position I am denoting by uxt, and if you take the horizontal distance, this is the horizontal line, and if you take the horizontal distance, this is your horizontal distance x. So if the time is t and if the horizontal distance is x, then what is the position of this element when these two parameters are given? What is the position u of the of any element of the string? So we are interested in finding an equation which, with the help of which we can find out this u. So this is basically the problem. You can define this problem in terms of the problem of vibrating string, or you can define it as a mathematical problem. Both of them are equivalent. Now the question, why the when we actually complete the derivation of this article, in the end you will see that we will get an equation, and that equation will be called a one-dimensional wave equation. And why is it called a wave equation? The equation as a result in the end which will be obtained, that why is it called a wave equation? The reason is that it represents fluid surfaces. For example, water waves. So that the equation which we obtain in the end, that will represent the waves which are produced in water. And why is it called a one-dimensional wave equation? Because we are considering only x, which is the horizontal distance. So we are considering only one dimension, which is the horizontal dimension. We are not taking other dimensions, vertical dimension, we are not taking that. So there is only one dimension that we are considering. So what we obtain in the end will be a one-dimensional wave equation. Now coming back to the problem. Now before we actually model the whole problem, we'll make certain assumptions. And why are we making these assumptions? We make these assumptions just to simplify our model. So whenever you are modeling a problem mathematically, you make certain assumptions. just to simplify your model. So I make these assumptions. The first assumption that I make is the tension in the string. I'll explain to you the whole, the assumptions I'll explain to you one by one, but let me just read out the first assumption. The tension in the string is always in the direction of the tangent to the existing profile of the string. Now this was the original string before you plugged it, before you applied force on it, and when you applied force on it, the string started moving up and down. Now because you have applied a force on it by plucking it, so consequently the string will also produce an equal and opposite force. For example, when you have a rubber band and when you pluck it, then you can feel that the rubber band is stretched. You are plucking it and the rubber band is getting stretched. So there is a tension which is being produced in the rubber band. In the same way, when you are plucking the string, as a result, as a response to it, an equal and opposite force is created in the string itself, and that force is called tension. And the first assumption that we are assuming is that the tension T which is produced in the string as a result of the force that we have applied by plucking it, this tension acts along the tangent to the existing profile of the string. So this is the string which is moving up and down. This is the profile of the string, and the tension acts in the direction of the tangent. So this is the tangent. So this is, I hope I'm able to draw the diagram properly. So this is the tangent, and the tension acts along the tangent. This is the first assumption that we are making. The second assumption that we make is that this tension T, which is the equal and opposite force that is created in the string after you pluck it, this tension T is constant. The third assumption, the weight of the string, let's just suppose that the weight of the string is W. So the weight of the string, this is the string which is tied at two ends, and the weight of the string acts in the downward direction. We all know that the weight is nothing but a force acting in the downward direction. So the weight of the string, which is W, is very small. So that is why I'm putting so many less than signs. It's very small as compared to the tension T. The deflection is small as compared to the length of the string. Now, what is the deflection? When you pluck this string and it starts moving up and down, so this is the deflection. How far it can go up, how far it can go down. So this is the deflection in the string. So I'm assuming that the deflection in the string, this particular deflection, this deflection is very small as compared to the length of the string, which you can see. We are assuming this. And fifth assumption, that the slope of the displaced string, the string will be called a displaced string because you have displaced it. You have applied force on it. So the slope of the displaced string, this is the slope of the displaced string. This is very small. If slope we denote by m, slope of this string we denote by m, then this m is very small as compared to unity, as compared to 1. So it is very small as compared to this one. And the last assumption that we make is that there is only pure transverse vibration, which means that when you pluck the string, this particular string, when you pluck it, then the string just moves up and down, like this, up and down. This is the only motion or only vibration which the string can have. Although in actual the string might have other vibrations also, but just to simplify our model, we are making this assumption. So basically, these 6 assumptions we make: the tension acts along the tangent, the tension in the string is constant, the weight of the string is very small as compared to the tension, the deflection is very small as compared to the length of the string, and the slope of the displaced string is very small as compared to 1, and there is only pure transverse vibration, no other vibration. So after we make these 6 assumptions, we are now going to derive the equation of motion, which will help us to find out the position uxt of any element of the string at the time t, and eventually in the end what we will obtain will be called a one-dimensional wave equation. So this is the end of the first part. Okay, let me start with the derivation of the one-dimensional wave equation. Let me start with the problem that I started with. This was a string, and we assume that the length of the string is L, and the string is fixed at the two ends. So it has fixed end points. And now what you did was that you gave you applied a force on this string, you plucked this, and the string was displaced and it started moving up and down. There were vibrations that were produced in the string and it got displaced. So what we are going to do now is to derive the one-dimensional wave equation. Instead of considering the whole string, we are just going to consider a very small element, and I'm calling this small element as AB, and I'm going to study this small element AB, and I'm going to derive the whole one-dimensional wave equation with the help of this small element AB. So consider a differential element AB, a small element AB of the string. So this is the small element AB, and I have drawn this small element AB in a magnified form. So this is the magnified form of this small element AB, which is a part of the string which is displaced. Now this small element AB, if you just see the whole diagram, I'll explain. The origin, this is the x-axis, this is the u-axis. U is nothing but the position of the string, of any element of the string at time t when the horizontal distance is x. This I have already explained. So this is the u-axis, this is the x-axis, this is the small element AB, and because you are displacing the string, because you are plucking the string, applying a force on it, therefore tension tension is produced in the string, and this tension we are calling as T, and we have already assumed in one of the assumptions that the tension acts along the normal to the string. So tension is acting at this point, the tension is acting at in this direction, and at this point A, the tension is acting at this direction. So it is acting along the tangent to the string. So this is the tension here, T, and this is the tension at this point. So consider a differential element AB of the string. This whole diagram I have explained. And now if you drop a perpendicular, these two are perpendiculars. This distance, this horizontal distance, let us suppose this is x. And because this is a very small element, so this this particular distance is x plus delta x. So this particular distance is delta x, which is very small, or you can call this as del x. So this is a very small distance. So let T be the tension at the endpoints. T is the tension at the endpoints. T is constant. Tension is constant. Again, there was an assumption, if you remember. Tension is constant. So the tension which is acting at this point is same as the tension which is acting at this point. And I'm assuming that the tension T makes an angle beta here with the horizontal axis, and the tension T here makes an angle alpha with the horizontal axis over here. So let T be the tension at the endpoints. The forces acting on the element of the string in the vertical direction are, I'm interested in calculating what is the force which acts in the vertical direction. So this is what, this is the resultant force which acts in the vertical direction, T sine beta minus T sine alpha. Now from where is this coming? Now if you just see, this is the tension T which is acting at this point B, and if you just resolve this tension T, the angle which it makes with the horizontal axis is beta. So if you resolve this vector T along the horizontal axis and along the vertical axis, so this part of the force T, this is nothing but this is T cos beta, and this is nothing but T sine beta. And this part comes from mechanics. Those who have studied physics or at some point in their 11th or 12th, or those who have read mechanics, they know how to resolve a force. So when you resolve this force, tension is nothing but a force, and when you resolve this tension along the horizontal axis, this is the component of tension which acts along this is the force acting along the part of T which is acting along the horizontal axis, and this part of T is nothing but T cos beta, and the component of the tension T acting along the vertical axis is nothing but T sine beta. So you can remember it actually like this. Actually, if you have a right angle triangle, and if this is the angle theta, and if this is your F, you want to or this is your hypotenuse H, let me call it as H, and this is your P, and this is your B. If you want to calculate sine theta is what? P by H, and cos theta is nothing but B by H. So if you want to calculate P, what is your P? P, if you just see from here, P comes out to be H sine theta, and from here B comes out to be H cos theta. So this perpendicular is nothing but H, this perpendicular is nothing but H sine theta. So along the vertical direction you can see it is H sine theta, and along the horizontal direction this is nothing but H cos theta. Same here. along the vertical direction, instead of h I have t, and instead of theta I have written beta. So along the vertical direction means perpendicular direction, the component is t sine beta, which is same as h sine theta, and along this is along the vertical direction, and along the horizontal direction the component of t which I have written is t cos beta. Here this is along the horizontal direction, the base, it is h cos theta. These two are comparable, so you can remember it like this. Anyway, but for those who have done physics at any point in their school, or if you have read mechanics, then you know that when you resolve a vector along the vertical axis, then the component of that vector, let's say vector or force, the component of this force t along the vertical axis is t sine beta, and the component of t along the horizontal axis is t cos beta. So you can remember this. So here similarly the same thing goes for this. If you resolve this tension along the horizontal axis, so I can write this over here, this is nothing but this is t cos beta. This is the component of t acting along the horizontal axis, and this is the component of t acting along the vertical axis. So this is t sine beta. The same way, if you resolve this vector t along the horizontal axis and along the vertical axis, so along the horizontal axis the component is going to be t cos alpha, because here the angle which t makes with the horizontal is alpha, and the component which is acting in the downward direction, this is t sine alpha. This is t cos alpha, t sine alpha, t sine beta, t cos beta. So these are the, so this is how we have resolved t along the horizontal and the vertical axis at the point A and B. So, so when you want to calculate the total force acting in the vertical direction, so what are the two forces acting in the vertical direction? So this is t sine beta, which acts in the upward direction, and this is t sine alpha, which acts in the downward direction. So if you calculate the resultant force is going to be t sine beta minus t sine alpha. Why minus? Because t sine alpha acts in the downward direction. So this is the total resultant force acting in the vertical direction. Now we apply Newton's second law of motion. What is Newton's second law of motion? Again, those who have read physics at some point in their schools, or if you are already aware, even if you are not aware, but still I can explain to you what Newton's second law of motion is. Now Newton's second law of motion says that force is equal to mass into acceleration. This was Newton's second law of motion. So force we have already calculated, the force in the vertical direction we have already calculated. This is the force in the vertical direction, and then again the mass into acceleration, we have to calculate what is mass into acceleration. Mass into acceleration is given by this particular expression. This is the force which we have calculated in the vertical direction, and this is mass into acceleration. Now what is your rho? Rho is nothing but this is the line density. Line density is nothing but it is the mass per unit length. Mass per unit length. Mass per unit length means this is the mass of 1 unit length of the string. And what is delta S? Delta S is nothing but this is the arc length of the element of the element AB. So we are assuming that the length of this element AB is nothing but delta S. So what is the rho is the mass per unit length, mass of 1 unit of length, and this is the total length of the element. So total mass, if you want to calculate it, it's going to be nothing but rho into delta S. This is the mass of 1 unit, and this is the total length, mass of 1 unit of length. This is the total length. So this is the total mass. So this factor is playing the role of m, and then this factor is playing the role of acceleration. Why? Because you have already explained u is nothing but u represents the position of the string at position. U is nothing but the position. So when you calculate the derivative, when you calculate the partial derivative of u with respect to t, if you differentiate u partially with respect to t, then what you get is velocity. And if you differentiate u with respect to ut with respect to t again, which means that if you calculate utt, then utt represents nothing but acceleration. So u is position, ut is velocity, and utt denotes nothing but acceleration. So this factor is playing the role of acceleration. So this is mass into acceleration. So total force in the vertical direction is nothing but this is the this is equal to mass into acceleration by Newton's second law of motion. This is what Newton's second law of motion says, that force is mass into acceleration. So this equation I'm marking as 1. So now once you have reached at this point, now coming to this point that the slope of the displaced string is very small. This is an assumption which we made in the beginning, that the slope of this displaced string is very small as compared to unity. It is very less. So because the string is something like this, let me write over here. The element of the string is like this. This is the element of the string AB. This is the element of the string AB like this, and here, this, let us suppose this is the angle of inclination theta, and this is the horizontal axis. So I'm saying that the slope is very small, and how, if you denote slope by m, then slope is given by tan of angle of inclination. So tan of theta, I'm saying that this is very small, approximately equal to 0, and if tan theta is approximately equal to 0, this means theta is approximately equal to 0, and if theta is approximately 0, this means that this, in a way, this element is in a way like this. It is almost coinciding with the horizontal axis. In a way it is like this, because theta is approximately 0. Since the slope is small, so tan theta is approximately 0, so theta is approximately 0. So this particular element AB coincides approximately with the horizontal axis, which means that this delta S, which is the length of the string, this is almost same as delta X, which is this. So this is what I am assuming, that delta S is approximately equal to delta X. So this I am marking as equation 2. Now coming to so the next thing that we have is that the angles alpha and beta are small. This is another assumption that we are making, that the angles alpha is the angle which the tension T here makes with the horizontal axis at the point A, and the angle beta is the angle which the tension T makes with the horizontal axis at the point B. So we are assuming that these angles are very small. Now with this assumption, when you make such an assumption, then there are two conclusions that you have, that sine alpha is approximately equal to tan alpha in that case, and sine beta is approximately equal to tan beta in that case. This again can be understood easily by just considering a right angle triangle, and if you have, this is theta, this is perpendicular, this is base, and this is hypotenuse, then I know that sine theta is this P by H, then cos theta B by H, and tan theta P by B. So these are the formulas. Now you can just have a look over here. If theta is small, then the diagram can be correctly drawn like this, because theta is small, so somewhat like this. The diagram is somewhat like this. Just because theta is very small, approximately equal to 0. This is your this is your perpendicular. This is your base, and this is your hypotenuse, and this was your tan theta. So if theta is very small, you can just see that this hypotenuse is almost equal to the base. And if hypotenuse is almost equal to the base, because theta is very small, the hypotenuse and the base are in a way coinciding. So if theta is very small, then hypotenuse is almost equal to the base. And if hypotenuse is almost equal to the base, then this tells me that I can make an assumption like this, that tan theta and sine theta are approximately equal. So that way, because this alpha and beta are small, so because alpha is small, so sine alpha is approximately equal to tan alpha, and because beta is small, so sine beta is approximately equal to tan beta. So this is the assumption that we are making. Let me just rub this off so that I can get a little space. Okay, so now once you have got these relations, this relation which was obtained from Newton's second law of motion, I have marked this as 1. This second relation, which in which I had assumed that this the length of this small element AB delta S is approximately equal to this horizontal distance delta X. This I have marked as 2, and this relation, these two relations I have marked as 3, that sine alpha is approximately equal to tan alpha and sine beta is approximately equal to tan beta. Now let me make use of 2 and 3 in 1. Just making use of 2 and 3 in 1, which means that I am going to substitute the value of sine beta and sine alpha as tan beta and tan alpha over here. and I'm going to substitute the value of delta S as delta X over here. So when I make these substitutions, this is what I get. T tan beta minus T tan alpha is equal to rho delta X UTT, and just dividing by T on both the sides, we get tan beta minus tan alpha is equal to rho delta X by T UTT. And in fact, this whole thing was done just to bring tan in picture. So these assumptions were made just to bring tan in picture and just to bring X in picture. And why have we brought tan in picture? Because tan can be related to slope and slope can be related to derivative. So this is what I'm going to do in the next step. Once you get this relation, which I have marked as 4, in this relation I'm going to replace these tan terms by slopes, and slopes again can be related to, can be replaced by derivatives, because we know that derivative at a point is given by nothing but the slope. So you can replace this by derivative, and finally u will come in the picture. So my aim is to bring u in picture so that finally you can get the one-dimensional wave equation, which is in terms of u. So now coming to tan alpha, let me find out the value of tan alpha. What is tan alpha? Tan alpha is nothing but the slope of the string at the point x here. And the slope is given by nothing but the derivative. U represents the position, so the derivative of the position u with respect to x at the point x. So this is given by, this is finally the value of tan alpha. All these results come from calculus. Tan beta, the time here is t. Tan beta is nothing but the slope of the string at the point x plus delta x here. And this slope is nothing but it can be expressed again in terms of the derivative. And so slope is given by the derivative of u with respect to x at the point x plus delta x. So these two relations I am marking as 5 and 6. Now let me make use of these two relations 5 and 6 and 4, which means I am going to substitute the value of tan alpha over here and tan beta over here. So when I make these substitutions, this is what I have. This is the expression which I have in terms of u. Ux x at the point x plus delta x t minus ux at the point x t is equal to rho delta x by t utt. Now again delta x, I divide by delta x, and this is the expression which I have. And now I'm interested in taking the limit as delta x tends to 0. Delta x is this portion, and I want to know what happens when I take this element as small as possible. If you take a very small element, then this delta x also will reduce accordingly. So I want to find out what happens to this equation when I take element as small as possible. So when this element becomes small, this delta x will also become small. It will tend to 0. So taking limit on both the sides. I'm taking limit on both the sides when delta x tends to 0. Taking limit on both the sides when delta x tends to 0, and when you take limit on both the sides when delta x tends to 0, this is nothing but this whole thing, this is the limit of ux. The function is ux, and you are taking the limit of ux ux at the point x plus delta x, and when you take the limit, this whole expression represents nothing but uxx by the definition of derivative again, and this portion is independent of delta x, so this will not get affected. So finally, this is the equation that you have. Uxx xt is equal to rho by t utt, and this particular equation can be written in this form. If you take t on this side and rho on this side, which means that I multiply by t on both the sides and divide by rho, we have utt is equal to c square uxx. I'm writing it in the opposite order. So here c square t by rho, I'm denoting by c square. So this is the final equation that I get. Utt is equal to c square uxx, and this particular equation is nothing but this equation is the one-dimensional wave equation which we were interested in. So this actually completes the article for derivation of one-dimensional wave equation. But one thing which I want to mention over here is that if you assume that there are this was the string which we were assuming, which is of length L, and if you assume that there are some external forces acting on this string, like resistance or gravitation or pressure or anything, then the equation, one-dimensional wave equation, takes a different form, something like this. The form which it takes is utt is equal to c square uxx plus f. So sometimes the equation can also be written in this form in case there is an external force acting on it. So that completes the article for the one-dimensional wave equation.